At the dawn of the 20th century, physics appeared confident, almost complete. The laws of motion laid down by Newton and the electromagnetic theory developed by Maxwell had explained planets, machines, electricity, and light with extraordinary precision. To many scientists, the universe seemed like a grand clockwork system, governed by continuous motion and predictable forces. Matter itself was thought to follow these same rules, and the atom, though invisible, was imagined as a tiny mechanical structure, obeying classical laws. Yet beneath this confidence, cracks were already forming, and nowhere were they more troubling than in the attempt to understand atomic stability and the strange behavior of light. According to classical physics, an atom consisted of electrons orbiting a positively charged nucleus, much like planets orbiting the sun. This picture felt intuitive and elegant. Electrons, carrying negative charge, were held in circular motion by the attractive electric force of the nucleus. However, classical electromagnetic theory carried a devastating implication. Any charged particle that accelerates must emit radiation. An electron moving in a curved orbit is constantly accelerating, which meant it should continuously lose energy in the form of electromagnetic waves. As it lost energy, the electron would spiral inward, eventually crashing into the nucleus. Calculations showed this collapse should occur in a tiny fraction of a second. If classical physics were correct, atoms would be violently unstable, and matter as we know it could not exist. This prediction stood in direct conflict with reality. Atoms were clearly stable. Tables, mountains, and human bodies did not collapse into flashes of radiation. Matter endured, unchanged over immense spans of time. This contradiction exposed a deep failure in classical theory. Physicists were forced to confront an uncomfortable truth. The laws that worked perfectly for planets and projectiles completely failed at the atomic scale. The atom refused to behave like a miniature solar system, no matter how appealing the analogy seemed. At the same time, another mystery was intensifying the crisis. When scientists studied the light emitted by heated gases, they expected to see a smooth, continuous spectrum of colors, as classical wave theory predicted. Instead, they observed sharp, discrete lines at very specific wavelengths. Each element produced its own unique pattern, like a fingerprint made of light. Hydrogen, the simplest atom, displayed a particularly clean set of lines that had been measured with great precision. Classical physics had no explanation for why atoms emitted light only at certain frequencies and ignored all others. Attempts to explain these spectral lines using known laws failed repeatedly. If electrons could orbit at any distance and energy, they should emit radiation across a continuous range of frequencies as they spiraled inward. But nature did not behave this way. The spectral lines were exact, reproducible, and mathematically ordered. They suggested that something inside the atom allowed only certain energies and forbidden all others. This idea was profoundly unsettling because it contradicted the classical belief that energy could vary smoothly without restriction. The problem grew even more severe when scientists examined blackbody radiation, another phenomenon involving light. Classical theory predicted that a hot object should emit infinite energy at high frequencies, an absurd result known as the ultraviolet catastrophe. Once again, classical physics produced predictions that clashed violently with experimental evidence. Max Planck offered a desperate solution by proposing that energy could be emitted only in discrete packets, later called quanta. Though Planck himself initially viewed this as a mathematical trick rather than a statement about reality, it planted the seed of a revolutionary idea. energy at small scales might be fundamentally quantized. Despite Planck's breakthrough, the atomic model remained broken. The stability of atoms and the origin of spectral lines were still unexplained. Classical physics, once the pride of science, now seemed powerless in the microscopic realm. This was not a small technical problem, but a foundational crisis. If atoms could not be explained, then chemistry, materials, and much of the physical world rested on shaky ground. The failure of classical physics forced scientists to reconsider their assumptions about nature itself. Perhaps the atom was not governed by the same continuous laws that described everyday objects. Perhaps intuition, shaped by humans, scale experiences, was misleading when applied to the invisible world. This shift in thinking was slow and resisted. Many physicists hoped that minor adjustments could save classical theory, but experiment after experiment confirmed that something radically new was required. The inability of classical physics to explain atomic stability and light spectra revealed a deeper truth. The universe is layered, and different scales obey different rules. What works for planets does not necessarily work for electrons. This realization marked the beginning of a new era in science, one in which certainty gave way to probability, and smooth curves gave way to discrete steps. The atom was no longer a tiny machine, but a gateway to an unfamiliar and counterintuitive reality. It was within this atmosphere of confusion and intellectual tension that new ideas emerged, challenging centuries of established thought. The failure itself became a guide, pointing scientists toward a more accurate description of nature. By confronting what classical physics could not explain, physicists were pushed to abandon comfortable assumptions and explore deeper principles. The shock was not just scientific, but philosophical, reshaping humanity's understanding of matter, energy, and the limits of human intuition. When Niels Bohr stepped into the crisis of atomic theory, physics was at a breaking point. Experiments were revealing patterns that simply refused to fit into the smooth, continuous framework of classical laws. The idea that nature might behave differently at very small scales was already whispering through the scientific community, but no one had yet dared to fully embrace it. Bohr did not try to patch classical physics with minor corrections. Instead, he made a bold and unsettling proposal. Energy inside the atom is not continuous. It is quantized, existing only in specific, fixed amounts. This single idea would overturn centuries of assumptions and permanently change how humanity understands the microscopic world. To grasp why this idea was so shocking, it is important to understand how deeply rooted the concept of continuity was in physics. From motion to heat to light, energy was thought to flow smoothly, like water pouring from one container to another. There were no forbidden values, no gaps, no sudden jumps. If an object could have one amount of energy, it could also have any slightly larger or smaller amount. This belief was not merely theoretical. It was supported by everyday experience. A rolling ball slows down gradually, not in steps. A dimmer switch smoothly changes the brightness of a lamp. Nothing in daily life suggested that nature might operate in discrete chunks. Bohr challenged this deeply ingrained world. By suggesting that electrons bound to an atom could only possess certain precise energy values. These energies were not arbitrary but strictly defined. An electron could exist in one allowed energy state or another, but nothing in between. This was not a matter of technological limitation or measurement error. It was a fundamental rule of nature. The idea felt almost heretical. To many physicists, it sounded less like science and more like an admission of ignorance disguised as theory. Yet Bohr did not introduce quantization as a vague philosophical idea. He tied it directly to experimental evidence, particularly the spectral lines of hydrogen. These lines had been measured with astonishing accuracy, and their mathematical regularity hinted at an underlying order. Bohr realized that if electrons were restricted to specific energy levels, then transitions between those levels would naturally produce light of precise frequencies. Each jump would correspond to a specific packet of energy, released or absorbed as radiation. The discreteness of the spectral lines suddenly made sense. What made Bohr's proposal even more radical was that it deliberately broke with classical electromagnetic theory. According to classical physics, an accelerating electron must emit radiation continuously. Bohr simply declared that this rule did not apply within the allowed energy states. An electron in a permitted orbit did not radiate energy, no matter how violently it accelerated around the nucleus. This was not derived from classical equations, but imposed as a new principle. For many scientists, this felt like surrendering the elegance and logical completeness of physics. But Bohr argued that nature's behavior, not human preference, must dictate theory. The introduction of quantized energy levels marked a profound shift in how explanations were constructed in physics. Previously, one sought to explain phenomena by tracing continuous causes and effects through time. Bohr's model replaced this with a rule-based structure. Certain states were allowed, others forbidden, and the theory did not attempt to describe what happened during a transition between states. The electron was in one energy level, then it was in another. The jump itself was not described in classical terms. This absence of a visualizable process deeply unsettled scientists who were accustomed to mechanical pictures of reality. Despite this discomfort, the success of the idea was impossible to ignore. The calculated energy levels of hydrogen matched experimental data with remarkable precision. Spectral lines that had been catalogued for decades now fell neatly into place. What had once seemed like mysterious numerical coincidences were revealed as direct consequences of quantized energy. This was not an approximate fit, but an exact one, and it forced even the most skeptical physicists to pay attention. The implications of quantized energy levels extended far beyond hydrogen. They suggested that atoms themselves were structured in a fundamentally new way. The stability of matter, which classical physics could not explain, suddenly became understandable. If electrons could exist only in certain energy states and could not radiate energy while remaining in those states, then atoms would not collapse. Stability was no longer a mystery, but a natural consequence of quantization. Matter endured because nature forbade electrons from losing energy continuously. This idea also reshaped the meaning of measurement and prediction. In classical physics, knowing the position and velocity of a particle allowed one to predict its future motion precisely. In Bohr's framework, what mattered were the allowed states and the probabilities of transitions between them. The theory predicted outcomes without describing continuous trajectories in detail. This shift marked the beginning of a deeper philosophical transformation in physics, where certainty gave way to structured limitation. Quantized energy levels also hinted at a deeper unity between matter and radiation. Light was no longer merely a wave propagating through space. It was intimately connected to the internal structure of atoms. Each spectral line represented a dialogue between an electron and the electromagnetic field, mediated by discrete energy exchanges. This connection laid the groundwork for later developments in quantum theory, where particles and waves would become two faces of the same underlying reality. Bohr himself was aware that his model was incomplete. He did not claim that electrons truly orbited the nucleus like planets, nor that his postulates were the final word on atomic behavior. What mattered was that the idea of quantization worked. It captured essential features of nature that classical physics could not. In this sense, quantized energy levels were less a finished explanation and more a doorway into a new way of thinking. The shock of Bohr's idea was not limited to laboratories and lecture halls. It challenged humanity's intuitive understanding of the universe. The notion that nature operates through forbidden and allowed states, through jumps rather than smooth motion, contradicted common sense. Yet experiment after experiment confirmed this strange behavior. The universe, it seemed, was under no obligation to conform to human expectations. By introducing quantized energy levels, Bohr forced physics to abandon the comforting illusion of continuity at all scales. He revealed that at the heart of matter lies a world governed by rules that are precise yet profoundly counterintuitive. This realization did more than solve technical problems. It transformed the very language and logic of science. Energy was no longer just something things had more or less of. It was something nature dispensed in exact amounts, according to rules that could not be broken. This idea became one of the cornerstones of modern physics. Without it, quantum mechanics could not exist. Concepts such as atomic orbitals, electron shells, lasers, semiconductors, and even modern computing trace their origins back to the simple but radical assertion that energy levels are quantized. What began as a shocking proposal to explain spectral lines evolved into a universal principle governing the microscopic world. In the end, the true significance of Bohr's introduction of quantized energy levels lies not only in its explanatory power, but in its philosophical impact. It taught scientists that understanding nature sometimes requires abandoning visual intuition and accepting abstract rules. It showed that reality at its deepest level may be discontinuous, structured, and governed by limits that cannot be crossed. This lesson continues to shape physics today, reminding us that the universe is stranger, more subtle, and more disciplined than classical imagination ever allowed. The idea that electrons are allowed only in specific orbits was one of the most unsettling claims ever made about the structure of matter. Before this proposal, motion was understood as something free and continuous. A planet could orbit closer or farther from a star, a stone could be thrown at any speed, and an electron, by analogy, was expected to move wherever forces allowed it to go. Nothing in classical physics suggested that nature imposed strict boundaries on where a particle could exist. Niels Bohr's assertion that electrons were confined to particular orbits shattered this assumption and forced scientists to rethink what motion and stability truly meant at the atomic scale. In classical models, the electron's orbit was determined solely by the balance between attractive and centrifugal forces. Change the energy slightly, and the orbit would adjust smoothly. There were no preferred paths, only countless possibilities. Bohr replaced this freedom with restriction. He proposed that only certain orbits were permitted, and all others were forbidden. An electron could not slowly drift inward or outward. It either occupied one allowed orbit or another, with nothing in between. This was not a technical limitation or a result of experimental uncertainty. It was a fundamental rule of nature. The shock of this idea lay in its apparent arbitrariness. Why should nature allow some orbits and not others? Classical physics demanded explanations based on forces and equations of motion. Yet Bohr's orbits were defined by simple conditions imposed from outside classical reasoning. These conditions selected specific angular momenta and energies, effectively fencing electrons into invisible tracks around the nucleus. To many physicists, this felt like abandoning explanation in favor of prescription. But Bohr was responding to a deeper truth. Atoms behaved as if such restrictions existed, regardless of whether classical theory could justify them. The necessity of specific orbits became clear when confronting the problem of atomic stability. If electrons were free to move in any orbit, classical theory predicted that they would radiate energy continuously and spiral into the nucleus. Bohr's allowed orbits solved this problem in a radical way. Electrons in these special orbits did not radiate energy at all. They were stable by definition. The atom no longer collapsed because nature forbade electrons from occupying unstable paths. Stability was not achieved through delicate balance, but through strict limitation. This restriction transformed the atom from a dynamic, continuously evolving system into a structured entity with well-defined states. Each allowed orbit corresponded to a specific energy, and the electron could remain there indefinitely unless disturbed. The atom, once thought to be a miniature solar system in constant motion and radiation, became more like a ladder with fixed rungs. The electron could stand on one rung or another, but it could not hover between them. The idea of specific orbits also provided a natural explanation for atomic spectra. When an electron jumped from one allowed orbit to another, it emitted or absorbed light with an energy equal to the difference between the two orbits. Because only certain orbits were allowed, only certain energy differences were possible, and thus only certain frequencies of light could be produced. The sharp spectral lines observed in experiments were no longer mysterious. They were direct signatures of the allowed and forbidden structure within the atom. What made this idea especially disturbing was that it defied visualization. In classical mechanics, one could always imagine a particle moving smoothly through space along a well-defined path. Bohr's electron, however, seemed to vanish from one orbit and reappear in another without traveling through the space between them in any describable way. The transition itself was not governed by classical motion. There was no path, no trajectory, no time, evolution that could be drawn on a diagram. This challenged the very meaning of motion. Physicists struggled with this conceptual leap. How could an electron move without moving through intermediate positions? How could nature permit such discontinuous behavior? Bohr did not claim to know the underlying mechanism. Instead, he insisted that the model described what could be observed and measured, not what could be imagined. This marked a turning point in scientific thinking. Explanation began to shift away from mechanical pictures toward abstract rules that captured experimental reality. The restriction to specific orbits also hinted that classical notions of space and time might not apply at atomic scales. If electrons could occupy only certain paths, then the geometry of motion itself was quantized. Space around the nucleus was not equally accessible to the electron. Some regions were allowed, others forbidden. This idea quietly undermined the classical belief that space was a neutral stage on which motion unfolded freely. At the atomic level, space itself seemed structured by hidden rules. As experimental techniques improved, the success of Bohr's orbits reinforced the idea that these restrictions were real. Calculations based on allowed orbits predicted spectral lines with astonishing accuracy, especially for hydrogen. This precision left little room for doubt. The model worked not because it was philosophically satisfying, but because nature appeared to follow its rules exactly. The discomfort it caused was outweighed by its explanatory power. Yet even as the model succeeded, its limitations became apparent. The notion of electrons moving in neat circular orbits could not fully explain more complex atoms or finer experimental details. Nevertheless, the core idea survived. Electrons do not have unlimited freedom. They are constrained by quantized conditions that define where and how they can exist. Later, quantum mechanics would abandon the idea of orbits in favor of probability distributions, but the principle of restriction remained intact. Allowed states replaced allowed orbits, but the shock endured. The concept of specific orbits also reshaped the philosophy of science. It demonstrated that physical laws need not align with human intuition to be true. Nature was free to impose rules that seemed strange, arbitrary, or even irrational from a classical perspective. The role of the scientist was no longer to demand that nature behave sensibly, but to discover and accept the rules it actually followed. This realization had far-reaching consequences. Chemistry, which depends on the arrangement of electrons in atoms, gained a new foundation. The periodic table began to make deeper sense, as electron arrangements followed structured patterns derived from allowed states. Bonding, reactivity, and molecular structure could all be traced back to the restricted behavior of electrons. What began as a shocking idea about orbits evolved into a unifying principle across multiple sciences. On a deeper level, the restriction of electrons to specific orbits forced humanity to confront the limits of classical determinism. If electrons could not move freely and continuously, then the future behavior of atomic systems could not be predicted in the same way as planetary motion. This opened the door to probability, uncertainty, and the abandonment of absolute predictability. The universe, at its smallest scales, was not a smooth machine, but a system governed by precise yet counterintuitive rules. The emotional impact of this shift should not be underestimated. Many physicists felt a sense of loss as familiar concepts crumbled. The comfort of visual models gave way to abstract mathematics and postulates, yet there was also excitement. The strange restrictions imposed by nature hinted at a deeper order, one that was hidden but exact. Each allowed orbit was not a limitation but a clue, pointing toward a more fundamental theory waiting to be discovered. In retrospect, the idea that electrons are allowed only in specific orbits stands as a bridge between classical and quantum thinking. It preserved just enough of the old imagery to remain accessible while introducing a principle that broke decisively with classical freedom. It taught scientists that continuity is not a universal truth, and that restriction can be more fundamental than motion itself. The shock of this idea did not fade with time. Even today, it serves as a reminder that reality at the smallest scales operates according to rules that defy everyday experience. Electrons do not wander aimlessly through atoms. They obey strict conditions, occupy defined states, and change those states in sudden, discrete ways. This insight, born from the proposal of specific orbits, continues to shape our understanding of matter, energy, and the hidden architecture of the universe. The moment Niels Bohr's atomic model successfully explained the spectral lines of hydrogen marked a turning point in the history of science. For decades, these lines had stood as one of the most precise and puzzling experimental facts in physics. When hydrogen gas was excited, it emitted light at a few exact wavelengths, forming a pattern that could be measured with extraordinary accuracy. These lines were not random. They followed simple mathematical relationships discovered by spectroscopists long before anyone understood their meaning. Classical physics, despite its success elsewhere, had no explanation for why hydrogen spoke in such a limited and orderly language of light. Before Bohr, these spectral patterns were treated as mysterious numerical coincidences. The Balmer formula, which accurately predicted the visible lines of hydrogen, worked astonishingly well but lacked any physical interpretation. It was a rule without a reason. Physicists could calculate where the lines would appear, but they had no idea why atoms emitted light only at those specific frequencies. This gap between mathematics and physical understanding was deeply troubling. A formula that predicted nature so perfectly yet explained nothing challenged the belief that science should provide causal stories, not just numerical fits. Bohr recognized that the answer lay inside the atom itself. He proposed that the hydrogen atom could exist only in certain energy states, and that light was emitted or absorbed when the atom transitioned between these states. Each spectral line corresponded to a specific jump between two allowed energy levels. The frequency of the emitted light was determined by the energy difference between those levels. This simple but radical idea transformed the spectral lines from unexplained curiosities into direct evidence of the atom's internal structure. What made this explanation so powerful was its precision. Using his model, Bohr derived the exact values of hydrogen's spectral lines from first principles. The calculated frequencies matched experimental measurements with remarkable accuracy. This was not an approximate agreement or a qualitative trend. It was an exact numerical match, down to the finest details measurable at the time. Such precision was impossible to ignore. It demonstrated that the model was capturing something fundamentally true about nature. The success of this explanation shocked the scientific world because it contradicted classical expectations at every step. According to classical theory, an electron moving around a nucleus should emit radiation continuously, producing a continuous spectrum of light. Bohr's atom did the opposite. It emitted light only at discrete frequencies, and it did so only during sudden transitions. The atom was silent while the electron remained in an allowed state, and spoke only when it jumped between states. This behavior had no analog in everyday experience. The explanation of hydrogen's spectral lines also provided a crucial test of the idea of quantization. It showed that quantized energy levels were not just a mathematical convenience, but a physical reality. Each spectral line represented a specific quantum of energy released or absorbed. The atom was no longer a black box that mysteriously produced light. It was a structured system with internal rules that could be read directly from its emitted radiation. This achievement had profound implications for the relationship between theory and experiment. For the first time, an atomic model made precise, testable predictions that matched experimental data perfectly. This restored confidence in theoretical physics at a time when classical theory was failing. It showed that bold, unconventional ideas could succeed where conservative approaches had failed. The lesson was clear. Fidelity to experiment mattered more than loyalty to established principles. The hydrogen spectrum also became a proving ground for new ideas about the nature of light and matter. Bohr's explanation suggested that light was exchanged in discrete packets, reinforcing the emerging concept of photons. At the same time, it revealed that matter itself had an internal quantized structure. Light and matter were no longer separate domains governed by different rules. They were deeply intertwined, communicating through precise energy exchanges. The simplicity of hydrogen played a crucial role in this breakthrough. As the simplest atom, with only one electron, hydrogen offered a clean testing ground for new theories. The success of Bohr's model here suggested that the underlying principles were correct. even if the model itself was incomplete. More complex atoms would require more sophisticated theories, but the core insight, that spectral lines reflect quantized energy transitions, would remain central. The emotional impact of this success was enormous. Physicists who had struggled for years with unexplained spectral data suddenly saw order emerge from confusion. What had seemed like arbitrary lines on a photographic plate now appeared as direct messages from the atomic world. Each line told a story about an electron changing its state, releasing or absorbing a precise amount of energy. The atom, once invisible and unknowable, became something that could be studied and understood through its light. This explanation also reshaped the way scientists interpreted experimental data. Spectroscopy was no longer just a tool for identifying elements. It became a window into the internal workings of atoms. By analyzing spectral lines, physicists could infer energy levels, test theoretical predictions, and explore the quantum structure of matter. This transformed spectroscopy into one of the most powerful techniques in modern science. The success with hydrogen exposed the limitations of classical thinking in a dramatic way. It showed that even the simplest atom could not be understood using continuous models of motion and energy. Discreteness was not an exception or a minor correction. It was a fundamental feature of reality. This realization forced scientists to reconsider the scope and authority of classical laws. At the same time, the explanation raised new questions. Why were only certain energy levels allowed? What determined their values? How did electrons transition between states? Bohr's model answered the what but not the why. Yet this incompleteness did not diminish its importance. On the contrary, it pointed the way toward deeper theories. By revealing what needed to be explained, Bohr's success set the agenda for the next generation of physicists. The explanation of hydrogen's spectral lines also had lasting philosophical consequences. It demonstrated that understanding nature sometimes requires abandoning visual models and accepting abstract principles. The electron's jump between energy levels could not be visualized in classical terms, yet its effects were measured with extraordinary precision. Reality, it seemed, was governed by rules that were mathematically exact but conceptually strange. Over time, Bohr's model would be superseded by quantum mechanics, which replaced orbits with wave functions and probabilities. Yet the explanation of spectral lines remained intact. Modern quantum theory still explains these lines as transitions between quantized energy states. Bohr's insight survived even as the imagery surrounding it changed. This endurance testifies to the depth of his contribution. In explaining hydrogen's spectral lines, Bohr did more than solve a technical problem. He provided a new way of linking theory to observation, structure to signal, and mathematics to physical meaning. Light emitted by an atom became a direct expression of its internal order. This connection transformed atomic physics and opened a path toward a deeper understanding of the quantum world. The shock of this achievement lay not only in its success, but in what it revealed about the nature of reality. The universe at the smallest scales was not continuous, intuitive, or mechanically predictable. It was discrete, rule-bound, and profoundly precise. Hydrogen, the simplest element, became the messenger of this truth. Through its spectral lines, it revealed that the foundations of matter were governed by quantum rules, forever changing how humanity understood the physical world. The reshaping of modern physics brought about by Niels Bohr's atomic model was not a sudden replacement of old ideas, but a deep transformation of how scientists understood reality itself. Before Bohr, Physics was built on the assumption that the universe was fundamentally continuous, deterministic, and governed by laws that applied equally at all scales. Space and time were smooth, energy flowed without interruption, and motion followed precise, predictable paths. Bohr's model cracked this foundation and revealed that at the heart of matter, nature followed a different logic, one that demanded new principles, new language, and new humility from science. The most profound shift lay in the realization that classical physics was not wrong, but incomplete. Newton's laws and Maxwell's equations remained extraordinarily accurate for large-scale phenomena, yet they failed completely when applied to atoms. Bohr showed that the microscopic world required additional rules that had no counterpart in everyday experience. This forced physicists to abandon the idea of a single, universal description of nature and accept that different scales of reality obey different laws. This layered view of the universe became one of the defining features of modern physics. Bohr's atom also changed the way scientific explanations were constructed. Classical physics relied on visualizable mechanisms. Particles moved along trajectories, forces acted continuously, and effects followed causes in smooth chains. Bohr's model broke this tradition. It relied on postulates rather than mechanical explanations. Electrons occupied allowed states, transitions occurred in jumps, and certain processes simply could not be described in classical terms. Physics began to shift from telling stories about how things move to stating rules about what is allowed and what is forbidden. This shift had far-reaching consequences. It prepared the ground for quantum mechanics, where probability replaced certainty and observation itself became an active part of physical theory. Bohr's ideas taught physicists that demanding classical explanations at the atomic level was a mistake. Nature was not obligated to conform to human intuition. Instead, intuition had to be reshaped by experiment and mathematics. This philosophical lesson became as important as the technical success of the model. The impact of Bohr's work extended beyond physics into chemistry. The structure of the atom, once understood in terms of quantized energy levels, provided a new foundation for understanding chemical behavior. The arrangement of electrons explained why elements had distinct properties, why the periodic table was ordered the way it was, and why atoms bonded in specific ways. Modern chemistry, from molecular biology to materials science, rests on principles that trace directly back to Bohr's atomic insights. Technological progress was also transformed. Without the quantum understanding of atoms, there would be no semiconductors, no lasers, no modern electronics. Devices that define contemporary life, computers, smartphones, medical imaging, and communication systems depend on quantum principles that emerged from the revolution Bohr helped ignite. What began as an abstract attempt to explain spectral lines ultimately reshaped civilization itself. Bohr's influence also changed the culture of science. He encouraged openness to radical ideas, even when they conflicted with deeply held beliefs. His willingness to accept paradox and uncertainty inspired a generation of physicists, including those who would go on to develop full quantum mechanics. The Copenhagen interpretation, strongly associated with Bohr, emphasized the limits of knowledge and the role of measurement, further challenging classical notions of objective reality. Perhaps most striking was how Bohr's work altered humanity's philosophical view of the universe. The classical dream of a perfectly predictable cosmos was replaced by a subtler vision. At fundamental levels, nature was governed by probabilities and constraints rather than certainties and freedoms. This did not weaken science. it strengthened it by aligning theory more closely with reality. Precision was achieved not through deterministic prediction of every detail, but through exact statistical laws. Bohr's model also demonstrated that progress in science sometimes requires accepting temporary models that are known to be incomplete. His atomic picture was not the final word, and Bohr himself acknowledged its limitations. Yet its success showed that a theory could be profoundly useful even if it was not perfectly accurate. This pragmatic approach became a hallmark of modern physics, where models are valued for their explanatory and predictive power rather than their philosophical perfection. The reshaping of physics was also a human story of resistance and eventual acceptance. Many scientists initially rejected Bohr's ideas as unnatural or mathematically unjustified. Over time, experimental evidence forced a change of mind. This process highlighted the self-correcting nature of science. Truth was not determined by authority or tradition, but by agreement between theory and observation, no matter how uncomfortable the implications. In the broader sweep of history, Bohr's atomic model marked the transition from classical to modern science. It closed one intellectual era and opened another. The universe revealed by modern physics was stranger, more abstract, and more constrained than anyone had imagined, yet it was also more elegant and deeply ordered. Bohr helped humanity glimpse this hidden order and accept that understanding reality sometimes means letting go of familiar ideas. The legacy of this transformation endures today. Every time physicists probe the structure of matter, explore quantum fields, or design quantum technologies, they build upon the conceptual shift Bohr initiated. His work taught science how to move forward when intuition fails, how to listen to experiment over expectation, and how to embrace the strange without abandoning rigor. In reshaping modern physics, Bohr did more than propose a new atomic model. He redefined what it means to understand nature. He showed that knowledge advances not by clinging to certainty, but by confronting mystery with disciplined imagination. The shock of his ideas echoed far beyond his own time, altering the course of science and forever changing how humanity sees the invisible foundations of the world.